So we've talked about in the past acids, and in this section we're going to go ahead and expound a little bit on what an acid and what a base are. Just talk a little bit about how we define these things and their properties. So one of the definitions for an acid is given by is called the Bronsted-Lowry definition. What it says is that an acid is a proton donor. So if you consider what hydrogen is, a hydrogen atom basically consists of one proton and one electron. So you got this helium atom, or not helium, hydrogen, with one single valence electron. So if you remove that one valence electron, remove it, it becomes an H plus ion. Well, all hydrogen is one proton, one electron, and so if you remove an electron, all that's left is a proton. And so an H plus is often synonymously used for proton, or proton is synonymously used for H plus. And so what an acid is it's something that actually donates protons. And specifically, when you put an acid into water, into an aqueous solution, it breaks apart into H plus protons, and then whatever's left over will have a negative charge, right? Because it's an ionic form. You got H plus and whatever minus. So this is a generic form. Notice there's no element symbol A. Not all acids are created equal, however. Some acids, when you put them into water, they ionize and they form 1H plus. These acids are called monoprotic acids, meaning one proton comes from them. Some acids, on the other hand, when they are put into water, they actually release two H plus ions and are called diprotic acids. And so you have these, there's also acids that when you put them in water, they break apart, they give off three H plus ions and called triprotic acids. Um, so there's also this definition, or this kind of category we place acids into, and that is the strong and the weak acid category. And there are 7 strong acids, and these are them listed below. You'll need to know these, by the way, for your next exam, so you'll be expected to know what all 7 strong acids are. So take time, use flashcards, and know which ones are strong acids. But let me give you a definition or the difference between a strong acid and a weak acid. So say you were to put 12 hydroiodic molecules into water. All 12 of them would break apart. If you were to put 12 weak acids into water, some of them would break apart, like do this transition up here where they break apart into H plus and A minus. But most of them would actually stay in this form, and so this reaction does not go to completion. In other words, most of it is in this form, and some of it breaks apart into these two forms, and those are what are called weak acids, the ones that don't completely what we call ionize or protonate the solvent. So weak acids are all the other acids, and they are the ones that do not dissociate completely. Bases are very, very similar to acids. They're kind of like the flip coin for acids. And I'm going to give you 2 definitions for bases. The first is the Arrhenius definition, which said that a base is a substance that increases the concentration of OH minus when dissolved in water. So that's aqueous specifically. So when dissolved in water, these things break apart. And notice the products. Notice this is not boron, by the way. This is just a generic base B cation. So you got a cation, your anion, this hydroxide group, breaking apart into B plus and OH minus. Okay, so this is the Arrhenius definition. But the Bronsted-Lowry definition goes back to the protons. So just like the acid is a proton donor, a base is a proton acceptor. And so what a base does is if you put it into water, it will grab one of those protons from the water and make OH minus. Okay? And so things that are Arrhenius acids can be Bronsted-Lowry acids, but not all Bronsted-Lowry acids are Arrhenius acids. Arrhenius acids specifically have to have an OH group. Okay, yeah, so it has to be an ionic compound, has to have an OH group. And there are strong bases and weak bases, just like there are strong acids and weak acids. Again, the strong bases are the ones that dissociate completely. So when you put these into water, they completely break apart. For instance, in this case, into calcium plus ions and OH minus ions. All of the strong bases are they're all hydroxide ions, so they're ionic compounds with hydroxide as the anion, and all alkali metals bonded with hydroxide ions are strong bases. Also notice there's strontium hydroxide, calcium hydroxide, and barium hydroxide are strong bases as well. If we go to the periodic table, you notice right here, so everything in this group 1A, all the alkali metals bonded to OH groups would be strong bases. And then the other three strong bases are these three here, calcium, strontium, and barium. And so this once, if you use the periodic table for the strong bases, you can actually just say, well, all of these guys bonded to OHs are strong bases, and then starting row 4 all the way down to barium are strong bases as well when bonded to hydroxide ions. All other bases are weak bases. And down here we have a little depiction of what's going on. This one is an example of a Bronsted-Lowry base that is not an Arrhenius base. Notice the base here is actually the ammonia. So ammonia here doesn't have any OH groups. It doesn't have this group at all anywhere in here. But ammonia is considered an Arrhenius base. And the reason why is that when you put ammonia into water, it will actually steal or borrow one of the hydrogens, one of the hydrogen nuclei from the water. The hydrogen will, of course, leave its electrons with this oxygen, but the proton will go over, bond to this NH3, and then become NH4+, and this will be OH-. So this is a classic example of an Arrhenius base. Now, one of the other things that we have to discuss is what happens when we add an acid and a base together. And specifically, when we add a strong acid and a strong base together, what are the products? Because you will be expected to identify these whenever you see them. So what happens when we add an acid and a base together is we always get two products. We get water as one of the products. Notice, and I want to point this out at this particular juncture, that water does not have an AQ sign. It's not aqueous, it's a liquid. It is actually the solvent that this reaction is going on in. Okay, so notice for this example right here, we have hydrochloric acid. Hydrochloric acid is a strong acid plus sodium hydroxide, a strong base, going to form a salt. And what is the salt? It is the cation of the base and the anion of the acid. And so if we were to actually break this apart and show what happens in solution, it would look like this. When this acid is put into solution, we get H+ ions and Cl- ions. And when this base is put into solution, we get the sodium+ ions and OH- ions. Then we have our little reaction arrow that shows what happens when these things are mixed together. Well, we still have sodium ions and chlorine ions, but we also get this water formation. And so notice that this NaClAq just means that we have sodium and chlorine ions in the solution. It doesn't actually mean those two things are connected or associated. These are still considered dissociated ions. And so if we cross out everything in here that is not the same on the left-hand side and right-hand side of the reaction arrow, we have chlorines that look exactly, chlorine ions that look exactly the same, and sodium ions that look exactly the same. And if we write everything left over, that is what we call the net ionic equation, where we have an H+ plus an OH- going to form H2O. By the way, I'll just share with you at this point, and we'll talk about this a little bit later, that these things that we've crossed out are what are called spectator ions because they are not involved in the reaction.